Select the major product of the following Diels-Alder reaction. And so Diels-Alder reactions always follow the mechanism that is drawn up here. So this is what we call a cycloaddition reaction. Specifically, it is a 4+2 cycloaddition, and that 4 comes from these 4 pi electrons, and the 2 comes from these 2 pi electrons. And you always form this 6-membered ring. And so what I like to do is I like to always number my system the same way. So on the diene, I always number those carbons 1 through 4. On the dienophile, carbons 5 and 6. And then what we need to do is just follow those 6 carbon atoms. And those are the only arrows. Nothing else changes in this reaction. So if we're trying to draw a Diels-Alder product, I would find the diene and label it carbons 1 through 4. Find the dienophile and label that carbons 5 and 6. In drawing the product, first draw this framework. If we follow these arrows, we're always going to end up with a pi bond between carbons 2 and 3. So when I put that pi bond in, I'm going to recognize that if I'm following this numbering scheme, that's carbons 2 and 3. And then I will simply continue numbering around the ring. So definitely we will have this cyclohexene framework. And then what we want to do is look at what we started with and said, okay, what substituents did we have? Because they should still be attached. Carbon 1 is unsubstituted. Carbon 2 has a methyl group. Carbon 3 has a methyl group. Carbon 4 is unsubstituted. So I'm going to place the methyl groups on carbons 2 and 3. Carbons 5 and 6 were part of a ring. So this ring structure should still be bridging them. So I should still have a ring here with 2 carbonyls. All right. And if I look at my options, there's really only one that matches, and that's option D. So I'm going to go ahead and circle that and then just take a quick moment to explain the stereochemistry here. So this is really just indicating that these are syn to each other. So they came from a cis alkene. And although we don't tend to determine cis and trans in a cyclic system, because they're usually cis, this is cis, right? Because the bonds of the alkene are pointing in the same direction. You've got hydrogens that are pointing in the opposite direction. And if I add those in, it's probably easy to see where it's cis. So that's where we're seeing that this is just indicating they're on the same side of the molecule.